So let's start off with some innocent little problem. Maybe this one. We set some boundaries here when t goes from 0 to 2. We got our parametric equations. I made a picture of the graph. We're trying to find the area. When t is equal to 0, I notice that my x is equal to 1, so this is my starting point. When t is equal to 2, I notice that y is or x is equal to 3, so I know this is my other boundary point. I'm going to go with green this time. So we're trying to find out this area right here. To do that, we take a generic little tiny square. We imagine cutting this up into infinite many little differential areas, such as that one, and I try to compute the area for that. The area for that would be the height times the base. The height would be the y value. That would actually be y minus 0, the vertical distance. And the base would be a dx, a small little tiny distance measured horizontally. That's a dx. That's my dA. And now all I've got to do is add it all up. The sum, so we have that dA is equal to y dx. And I'm going to slap an integral on both sides. I'm going to go with yellow. Slap an integral on both sides. And that's what we've got to do. Add up all the little areas. Are you afraid? Don't be afraid. You're in good hands. Alright, here's an issue here. We've got differential of x's and y's. We would like just one variable, either all x's or all y's. But wait, what if we change them all to t's? Just for fun. Could we? Yeah, we could. Y can be exchanged for a t square. Oh my goodness. What about the dx? Don't worry. X is equal to t plus 1. That would tell you that the differential of x would be equal to the differential of t plus 1. This is called slapping a d on both sides. That would give you that dx is equal to dt. Of course, d1 is 0. So the exchange rate for dx is the same thing as dt, making this one t squared dt. And what have I done here? I've changed my area not into x's or y's, but into t's. Beautiful. From 0 to 2, that would of course give you t to the third over 3, going from 2 to 0, which of course would give you 2 to the third over 3 minus 0. And that, my friends, would be your final answer. It's duck soup. Piece of cake. If you ever find a job where you get paid for doing stuff like this, take it. It's a good deal. Alright, I think that was too easy. I think we got to do another one because that was just ridiculously easy. Let's do another area problem. It's not fair. So let's maybe do something that is not that common. Have you ever found the area inside an ellipse? Everybody does circles, whatever. How about we try to do an ellipse? Okay? Find the area inside the ellipse. How about we plan out a strategy here? I'm thinking that we should focus all our attention here on this part. This part right here, this is called the first quadrant. If we could find the area here, we could just multiply it by 4 because we got 4 equal pieces. Right? So that's going to be our strategy. So I shall cut it up into infinite many little pieces that are infinitely small and red, just for fun. Infinite many pieces like this. And so each one of my little areas would be equal to the height times the base. The height would be equal to the y value. The base would be equal to a small little distance this way, not this way. This would be a dy. This would be a dx. This would be a ds. This is dx. So that's my small little area. Differential area is equal to y dx. And then I just add them all up with the great power and elegance of the fundamental theorem of calculus. Alright, the trouble here is that that you have x's and y's, same trouble as what we had before. So you'd want to convert it somehow. the area is equal to the integral of y dx. Let's the y's we should exchange for t's. That would give you 2 sine t. The dx, oh, this is kind of fun. dx is equal to negative 5 sine of t dt. So that would be negative 5 sine of t dt. Nice. And then maybe I'm going to try to write thinner so that more stuff fits. We're going to need a lot more board in this. A lot more space. Alright. Don't worry. Alright, so we've managed to exchange the dx. We exchanged it for the dt's. So that's this dx got exchanged for that many dt's. We factor everything out. That would give us a 2 times a negative 5. And of course I still have the integral of a sine squared t dt. I noticed that I need some limits on here. What should my limits here? When we were plotting this one, we noticed that t is equal to 0 starts off here. T is equal to 0. And of course this one gives you t is equal to pi over 2 or 90 degrees. Here's something interesting. When I did this a while back, when I first did it, I thought I should go from t equals to 0 to 90 degrees. But if I do that, I'm tracing the area backwards from right to left. That gave me a negative area. So why don't we try going this way, from left to right, so that we get a positive area. So we should go from 90 degrees to 0. That's how the curve is traced. It's traced this way. Incidentally, it might be instructive for you to play around when you plotted these. If you're just a beginner with parametric equations, try and see what happens if you switch these, or try and see what happens if you add a negative here, or if you add a negative on both. Those are fun questions. Essentially, what it does is it changes the starting point where you trace the circle, and sometimes it also changes the direction in which the circle is traced. Any case, in this case, we're going to go from 90 degrees from this point all the way to 0. And we shall do this carefully using our excellent integrating skills. This is our famous identity. Famous identity goes something like this. Sine squared theta is equal to 1 minus cosine 2 theta all over 2. So I exchanged that. The benefit here is that it has no squares. So I like to exchange this square for that version of it. So that would be times, I'll factor out this 1/2 integral of 1 minus cosine of 2t as dt as t runs from pi over 2 to 0. Alright, that would give me 2 times negative 5 times 1/2. I know what some of you may be thinking, why don't I just multiply 2 times negative 5 equals negative 10? Well, the answer is because I'm not a pattern hider. Pattern hiders, if you go on and do that, you will hide the patterns. If you leave it like that, you will expose and possibly not just solve this area of the ellipse, but all of them at once by exposing the pattern. In other words, maybe if you keep the 2 and the 5, you'll know what to do if this was a 7 and if that was a 13. Just saying. Keep it that way. Don't be a pattern hider. Alright, where were we? So this would be a t minus a 1/2 sine of 2t. If you're rusty on these, you should do a u sub. Derivative sine is cosine times the derivative stuff inside is 2. That's why you got to have that 1/2. And this is going from 0 to pi over 2. So that's going to give me a 2 times a negative 5 times a 1/2 times a pi over 2. Sorry, I meant plugging in the 0 times a 0 minus 0 minus pi over 2 minus 0. When you plug in pi over 2, you get sine of pi. You get something like this. This goes away. This gives you negative pi over 2. For a grand total of, I have 2 times negative 5 times 1/2 times negative pi over 2, which can be cleaned up just a little bit without pattern hiding. 2 times 5 times pi over 4. Yeah? 2 times 5 times pi over 4. The negatives are gone. So this one right here is 2 times 5 times pi over 4. Therefore, the whole area would be 4 of these. I have 1, 2, 3, 4 of these. 4, 2 times 5 times pi over 4. That, of course, would give you 2 times 5 times pi. That, my friends, is the area of an ellipse. Now, isn't that interesting? Take a moment. Savor the moment. Man, I gotta go get some more espresso. What do you suppose would go differently on this problem had this been a 7 and that been a 3? I have an amazing conjecture. I bet this would have been a 7 and that would have been a 3. In other words, this is what's amazing. We could summarize it like this. We could say something like this. If I have an ellipse where this is B and this is A, then the area is equal to B times A times pi. Whoa, 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 wait a minute. What if the ellipse also happened to be a circle where A and B are both equal to R? Because on a circle, both of these are equal. Everything is R all the way around. In that case, the area would, this formula would say that the area is equal to R times pi. Wait a minute. Is that equal to pi r squared? Oh no, we didn't. Yes, it is. So we verify that the ellipse formula that we just derived coincides with the expected formula for a circle when the ellipse happens to be a circle. Told you. See why they pay me? Alright, that was fun. What else have we got? Arc length. Alright, come back and we'll do some arc length. Alright.